Good morning, everyone. Good morning, our students. Good morning, our professor.
Good morning.
I'm glad to welcome you to our lecture. And we hope that the lecture will bring you a lot of interesting and new knowledge. If you have any question, you can ask. Okay, welcome.
Okay, thank you. Shall we start from now? Okay, okay, then we can start. Maybe I should share the screen with you guys. Hello, everyone. Can you see the slides?
Yes, Professor.
Yeah, okay. Okay, thanks. Okay, then we can start from now. Okay, good morning, everyone. I'm very glad that I can have this opportunity to share some interesting, as from personally, I think it is interesting topics with you guys. My background is from pharmaceutical science, so I would like to. I'm not sure how many of you guys have the same background, and but basically, I was told most of you are from have the background of pharmacy, so I'm sure this would be a very interesting topic for both of us. The title for today's talk is poorly water-soluble drugs and the strategies to improve their oral bioavailability. And today we are going to focus on the amorphous systems. So basically, amorphous solid dispersions and amorphous and also co-amorphous systems. So let's start. First of all, I would like to introduce myself to you guys. I got my PhD degree from University of Copenhagen in the year 2019. In Denmark. Denmark is a very beautiful country, and the University of Copenhagen is also very nice. I got my PhD in pharmaceutical science. Before that, I got my bachelor and master degree from Sichuan University. Sichuan University located in west of China, Chengdu. I'm sure some of you maybe know a little bit about this city. This city is famous for its delicious food, and also it is the hometown of the pandas. So if you guys have the interest to come to China, and Chengdu would be a very nice option for you guys. And I also have some experience from the industry. Before I came to Wenzhou Medical University, and this is my current position, and I also worked as pharmaceutical researcher in some companies, both in Chinese companies and also some international companies in Abbeville, Germany, and also Chengdu Huide Pharma as a pharmaceutical researcher, trying to develop some new formulations and also some general products for these companies. So I have the background from also both academia and also industry. This is the outline for today's talk. First of all, I would like to introduce you some general information about the poorly water-soluble drugs, and then you focus on the amorphous and other strategies to improve the water solubility of these drugs, and also to improve the bioavailability of after oral administration. So first of all, this is some books. I think it may be some of you have the interest. You can have a look afterwards. Formulating poorly water-soluble drugs and amorphous solid dispersions and so on. These books are very interesting, and I also will give you a a good picture of the whole area of this topic. And this is a basic background. We can see from here, this figure shows the number of new drug approved into the market. This is each year, okay, from 1992 to the year 2011. Of course, there are some new information in recent years, but I didn't find some this new information. So, but basically, we can have a look at the trend of the R&D department, R&D development. As we can see, the number of the new drug approved each year is decreasing, right? And basically, of course, there will be a little bit changing, but the basic trend is decreasing, and the yellow curve shows us the costs, right? The costs of to develop each drug into the market. The cost of each drug we can see is increasing year by year, right? And until now, the year 2021, then the cost is much more expensive than this figure shows. So basically, we can see from this figure, it is more and more difficult to develop new drug. And also, it is, at the same time, it is become more and more expensive to develop a new drug. So this is the basic background in the industry. For the main topic, we are going to talk about pouring water-soluble drugs, right? First of all, I would like to introduce you some basic information about water solubility comparison. This have an example. The first figure, we all know that, right? A calcium carbonate. This we all know the solubility, the water solubility of this compound is very, very low. And I found the information from a paper here, showed here, is 13 micrograms per milliliter at room temperature. So basically, this is a very, very low solubility, right? And then mebendazole, this is a drug already in the market. I would like to ask you guys, have a rough guess. How do you think? What is the water solubility of this compound, this mebendazole? You can have a guess. You have no idea, but you can have a guess, right? And the value is 0.5. 0.5 microgram per milliliter. This number is from my experiment. So I checked it at the same condition, the same temperature and the same medium, right? So comparing these two compounds together, we can see that the solubility of the mebendazole is even much lower than calcium carbonate. So basically, we will know the calcium carbonate like a stone, right? We can see a lot of stones in the sea, in the water, but this drug, mebendazole, the water solubility is much lower. So as from this example, we can have a rough idea. Some drugs, even though they are already in the market, some drugs. The solubility of some drugs is very, very low, much lower than your imagination. You can imagine this kind of compounds, you can take it orally, and then because they cannot be dissolved in water, basically it cannot be absorbed by your body, right? So for these drugs, the bioavailability of these drugs is very, very low. Sometimes it can be no more than 1%. In this case, it means over 99% of the drugs just get through the body and then they cannot be absorbed. So this is why improve the water solubility of these compounds is very, very important, both in academia research as well as in industry. Before we start, and I will introduce you a definition we call BCS. BCS, the full name of BCS is Biopharmaceutical Classification System. This is already this figure shows us. We can use two dimensions, solubility and permeability. These two dimensions, trying to classify all the different APIs or drugs into 4 classes. For class 1, these drugs usually shows good solubility and good permeability. Solubility, we all know solubility, what this means, right? But permeability, it means these drugs can get through your, for example, the cell membrane, and means it can be absorbed or not. Can be absorbed or not. So basically, these two dimensions are very, very important for drug getting into your body and have the pharmaceutical roles. So class 1 means good solubility and permeability. Class 2 means poor solubility and good permeability. In this case, for these drugs, usually the poor solubility is the key point of the low and variable bioavailability after oral administration. And then class 3, good solubility and poor permeability. This means permeability is the limitation, right? We should improve the permeability. And class 4 means these drugs shows poor solubility as well as poor permeability. So in this case, we have the different classifications, and then we for each drug, for a given drug, we can see what's BCA system belongs to, and then we have a rough idea what we should do to develop nice formulations. But the question is how we define it is soluble or permeable. In this case, we have 2 sentences here. Usually we have said a drug is considered highly soluble when the highest dose strength is soluble within 250 milliliters of water over a pH range of 1 to 7.5. This 250 milliliters, usually because most of the human beings, the volume of the human being's stomach is kind of like 250. So this is just like we define it like this. Why not at least 249? Why not 260, right? This is just we human beings define this. And permeable means that a drug, if a drug considered highly permeable, when the drug can, over 90% of the drug can be absorbed in human beings. In this case, we say this drug is permeable. So use this kind of table, we will see which drug belongs to which classes, and then we can see what kind of methods we should to use to improve and develop good and more suitable formulations. In this case, polywater soluble drugs usually belongs to class 2 and class 4, right? These two. And I have to share with you the information about the distribution of the drug in BCS system. For the marketed drugs, we can see BCS2 plus BCS4, both these 2 classes shows poor water solubility, right? And in this case, for marketed drug, usually basically it means 40% of the marketed drugs is water insoluble. And for the drugs under development, well, this drug we call it drug candidates. Drug candidates, we can see almost 17% of the drug candidates belongs to BCS2. This means these drugs candidates shows very low water solubility, right, and good permeability. And the BCS4 it is around 20%. Basically, BCS2 and the BCS4, the plus together, almost 90%. In other words, almost 90% of the drugs under development or drug candidates is water insoluble. So we can see it is super important, right? It is super important to improve this water solubility of drugs of these compounds. And also for the marketed drugs, it is also very meaningful trying to improve the water solubility of these drugs, because we can using this way to improve the bioavailability of these drugs after oral administration. For example, if a drug belongs to BCS2 system and it is already in the market, basically the market commercial products, their bioavailability is around 20%. And then if you can increase it to 50%, this would be very nice, right? For the potent water soluble drugs, there are BCS2 and BCS4. Basically, for the BCS4, we can see it is like brick dust, and the BCS2 drugs. BCS2 drugs usually they have the poor solubility, but with higher permeability. And in this case, it's kind of like brick balls. So both BCS2 and BCS4 drugs, it is very important trying to improve their water solubility, and the physical chemical properties determine formulation approach, because just use a very normal formulation approach, you cannot get a very nice or satisfied bioavailability. So this is why we are here today, right? So we are going to talk about how to improve and the strategies of improve the water solubility of these drugs. Here, this is a rough picture of different strategies. This strategy is basically from the book, actually Thomas Ratz from University of Copenhagen. This is he's a very famous professor in this area. If you have interest, you can just check this book. In this book, they also is trying to classify all different strategies into 3 levels. First of all, molecular levels. Molecular levels, we have also some strategies, for example, prodrugs, right? Most of you guys already know this, prodrugs, and salt formation, co-solvents, and so on. This is from molecular level. And also we have another particulate level. You can measure your particle size, right? To prepare a much smaller particles. And this we call the particle size reduction. And usually in the smaller particle size, the faster dissolution rates. And also using different polymorphs, we are going to talk in more detail a little bit later. And amorphous and coamorphous systems. And also the other level we call current level. You can prepare lipid solutions, emissions, macroemissions, nanoemissions, and so on, right? A lot of later technologies can be classified into this level. So we have all of different strategies to improve the water solubility of these drugs, but all of the strategies, they're not the specific strategy cannot be used for all the drugs, because both of them have their own advantages and disadvantages. For example, prodrugs. Prodrugs, sometimes you can get a very nice water soluble drugs, but it is a new compound, right? You need to do a lot of experiment to prove it is safe, it is effective. So basically, this takes a lot of money and time, as we already discussed. Salt formation means the compound, the drug candidates should be acidic or basic. For the neutral drugs, you cannot use salt formation to prepare more water-soluble compounds, right? So all these strategies, they all have their own disadvantages. So basically, we are focused on polymorphs and amorphous, coamorphous, these 3 strategies today. Okay, amorphous. What is amorphous? And then what is crystalline solid? So we are going to have to start with this section. These two pictures, I'm sure most of you guys have the experience, right? The coffee, you have a lot of sugar, and the right side they have we have the. For me, actually, I like to eat this kind of candies when I was a child. I'm not sure how many of you like this. All of us, we know this different kinds of sugar, but which one is sweeter? Which one is sweeter? And what the difference? The first one is crystalline sugar, and the second one is amorphous sugar. So which one is sweeter? Let's just leave it here, and then we will back here later. This is a drug already in the market in medicine. Some of you maybe know this, may know this drug in the medicine. In the medicine, intrinsic dissolution. Intrinsic dissolution. What this means? Intrinsic dissolution. This is a test in the dissolution rate of the compounds. This kind of dissolution test shows no in factors with no business with the particle size. And we don't have too much time to introduce in much detail, but you can have a look afterwards. This kind of dissolution test will give you a true dissolution rate of the compound, no business with the particle size. And for this sample, we can see black dots. Black dots is crystalline endomedicine. This is a time, right? 10 minutes, 20 minutes, 30 minutes, and this is the intrinsic dissolution rate. We can see from here these black dots and the red dots. The red dots is from amorphous endomedicine. We can see very obviously the dissolution rate of amorphous endomedicine is much faster than crystalline endomedicine, right? This is for an example of endomedicine. And here we'll show, let's discuss a little bit about solid drugs. Solid drugs, we have at least 3 different types: crystalline compounds, liquid crystalline compounds, and amorphous compounds. Crystalline compounds, usually they show very long-range order, right, in 3 dimensions. They have a very nice original structures. And amorphous compounds, they have no long-range order. They're just very messy, right? From the figure, we can see that. And the crystalline, you can see one by one, they have very in very nice order and arranged together. And the liquid crystalline scale just between these 2 different types, right? Between crystalline and amorphous compounds. Some of them is messy, some of them shows very nice orders. So this is the basic 3 types of the different compounds. And here we have a very nice technology to identify which types this compound belongs to. We named XRPD. The full name of the XRPD is X-ray port diffraction. And then using this technology, we can see from a lot of the peaks, right? A lot of peaks. This kind of the peaks is from the crystalline structure diffraction. So usually, if we see a lot of the sharp and high diffraction peaks, this means it is crystalline compounds. But if it is amorphous, they will show no diffraction peaks like this way, like this one. Figure C, from 10 to 30, like this, it's kind of like smooth. But when you zoom it up, you can see it is still not very smooth, but it doesn't matter. Compared to this one, right? It is much smoother. This we call halo. So using this technology, we can see or identify which kind of compounds it belongs to. From A, we can see this is from at room temperature. It is crystalline compounds, which shows very sharp peaks, right? And figure B, at a higher temperature, this is kind of like liquid crystalline compounds between this A and C, right? And sorry, the B is crystalline liquid crystalline compounds. And figure C, at higher temperature, you can see there's no non-range order, at least from 10 to 30, right? So this using this technology, we can see a lot of information from these compounds. And for amorphous and crystalline forms, different polymorphs, we can see from here, indomethacin, and this is a drug, and we already show you a few slides earlier. When you use quench-cooled method to prepare amorphous indomethacin, we can see from XRD results, you can see from 5 degree to 30 degree, there's no sharp peaks, right? You can see this we named, this is a very standard amorphous halo. And gamma indomethacin, this is form gamma. We know indomethacin have different polymorphs, right? Alpha, beta, gamma, and so on. So have the different polymorphs. This is from gamma. From gamma, we can see from different, they have the obviously different peaks. So this is very easy. We can see if you have a compound and you have no idea it is amorphous or not, you can just use XRPD, this technology, trying to characterize it, and then from the results you can see it is amorphous or not. And the polymorphs we already say indomethacin have different forms, and also the carbon we will learn, right? And carbon have at least 3 polymorphs, the diamond and so on, right? The three different polymorphs, and the different polymorphs usually shows totally different range order. The range order, what this means, we already talked about, right? The non-range order in 3 dimensions. If it is different, and then we can, it is different polymorphs. The same chemical structure, but with different crystalline structures. And in this case, we say, oh, this compound have different polymorphs. So different polymorphs, it is very important in pharmaceutical science or pharmaceutical industry, because you guys can have a look. There are so many different drugs already in the market, and there we have at least 2 polymorphs, but usually the commercial products use only one of the polymorphs. The polymorphs should be stable, will have a nice solubility or permeability, and so on. Basically, they will show totally different PK and PD after oral administration. So this is a very, very important definition in pharmaceutical science. Different solid forms we will discuss, except for polymorphs, we also have different other solid forms. We can see from here, this figure, different polymorphs, form A, form 1, form 2, form 3, or example, form 4, and so on. And this is the true polymorphs. There's true polymorphs. And amorphous system here, because you destroyed the crystalline structure of the true polymorphs, and then you will get amorphous phase. And except these 2, we also have a lot of different solid forms. For example, solvates, and these solvates you can see the hydrates or monohydrates or the dihydrates and so on, and co-crystal or salts. So this kind of also very common in pharmaceutical science. We name this different solid forms. Basically, today we are going to focus on the true polymorphs and amorphous phases. As we already discussed, the amorphous shows no non-range order because you destroyed the non-range order, right? So you already destroy it. And there's another technology usually is very useful in amorphous research and development. We named DSC. Some of you may have already used this kind of technology to do other experiments, and this is very useful. For giving products or giving sample, if you heat the sample, and then you will have different scanning signals. Here we have a very obvious stage here. This is belongs to if the sample is amorphous form, right? Amorphous form, usually you will see a glass transition. This is a glass transition, and after that, there's the sample, amorphous sample, recrystallized, and then you release the heat, and then you will observe a peak here. And after that, you will still going to heat the sample. You will see the sample is going to melting. And after that, there's some degradation, of course. So basically, from DSC, you can see a lot of information from this curve. Basically, we will take this glass transition. It's very important for amorphous form because of what? Amorphous form usually shows glass transition, and the glass transition temperature is very nice information to describe the physical stability of the amorphous systems. We will discuss in more detail later, because amorphous form usually they are not stable at all. But if we want to develop pharmaceutical products, we should make sure it is stable in the shelf time, right? At least for like 1 year or 2 years, they should be the same, right? If the amorphous form is not stable, this is not very good. So how we can see it is stable or not? Glass transition temperature is very important information. We can use this information trying to get a rough idea how stable it is. So we'll discuss later. And from crystalline samples, how to prepare amorphous, From crystal, like we can see from here, this is shows very nice orders, right? The crystalline structure is very, very nice, very beautiful. And then this is amorphous solid. Amorphous solid, you destroy the structure, and then this is very messy. But how we can prepare this amorphous solid? There are at least 2 pathways. First of all, the thermodynamic path. Using heating or dissolving. Using heating or dissolving, you can get a liquid melting or in solution. And then if you cool it down very fast, the cooling rate should be very high. Or if it is in solution, you just remove or dry the solvents as fast as you can, and then you will get amorphous solid. Because of what? Because these compounds, these molecules, they have no time to rearrange and recrystallize to form the crystal. Because your quench cooling, your cooling rate is very, very fast. They have no time to crystallize. And also, if you dry your solvents, is very fast enough, and also you can get amorphous solids. And this is the first method. The second method is kinetic path. You just use milling or other kinetic mechanic power, just destroy this crystalline structure. Right, destroy the crystalline structure, and then you will get amorphous solids. So basically, there are 2 normal methods or pathways to prepare amorphous solids, and we will discuss a more specific methods like ball milling, quench cooling, or spray drying, freeze drying, and so on. These are the kind of methods, but all of the methods belongs to path 1 or path 2, right? Amorphous intermediates can be prepared using different methods. As we already see, we can use different methods to prepare it, right? Quench cooling, QC means quench cooling, SD spray drying, and also ball milling, and color milling, and so on, right? We have if you start from different polymorphs, from alpha or from gamma, you can get different from different starting materials. all of them you can get amorphous indemnisation. This is from XRD results. We can see all of them shows no sharp peaks. This is just a halo, not a sharp peaks. So all of them are already amorphous. And using DAC methods, we can see this is a melting point, right? And this is a recrystallization. And before that, we can see this is some stage here. And this, I'm not sure if you can see it clearly, but there is a glass transition here, So basically, the temperature of the glass transition, we mean TG. TG is very important. From different TG, we can see maybe their physical stability is different. And also using chlorine indemnising different mean time from this is at the beginning. We can see this is the crystalline materials. Crystalline indemnising, and after 15 minutes of the meeting, we can see the peaks is in the intensity of the peaks is decreasing, right? Decreasing, and 30 minutes they're already almost amorphous. We can, but if we can still see a little bit peaks here in these places, and the 45 minutes basically it is already fully amorphous, right? And then maybe seven hours you can see this is a true amorphous. So basically, if you're using ball milling or other milling methods, using different ball milling term, you can prepare amorphous drugs. But sometimes you cannot use ball milling or milling method to prepare amorphous compounds. This depends, okay. And also we can see how much crystalline. What is the percentage of amorphous? So basically, we can see from these figures. And take home message one. The preparation methods. We have a lot of different methods to prepare amorphous compounds, but different preparation methods. Usually you will get different amorphous compounds. So this is we should know using different methods. You can prepare amorphous materials, but usually it is a little bit different. And then the third part, the drug polymer mixtures. Usually we name this also. You can see a lot of in other places. We call it amorphous solid dispersions or just solid dispersions. So this is kind of the drug polymer mixtures, and also including the preparation method. There are already some products in the market. For example, the amorphous. This is the pure amorphous APS because, as we already discussed, amorphous APS usually it is not stable, not physically stable, but some of them are stable. So it is okay to prepare pure amorphous, right? Pure amorphous like this full products. And for most of the amorphous drugs, it is not stable. So then in that case, we should use some polymers to stabilize the amorphous compounds. So for example, PVP, PEG, and so on, to stabilize the pure amorphous drug. So in this case, we also see some drugs already in the market. Basically, these companies usually like Roche and Bayer and AbbVie, these companies doing a lot of job already did a lot of job in this area. So most of the commercial products is from these companies. And I already discussed the stability of this compound, right? The stability of this compound usually we know. And here I will show you some two examples. Again, indemnising, as we can see from this figure, the raw crystalline emission, we can see the obvious crystalline peaks here, right? This is the starting materials. And if you prepare the amorphous, then we can see this rhythms, and this is amorphous. But the amorphous intermediate storage room temperature, just room temperature, not very high temperature. 1 week later, and then you can see this recrystallization peaks already showed. So in this case, 1 week is very short time. It's not possible, not allowed just for this sample. Only 1 week of stability, or it is totally not enough, right? And then this is a cimetidine. Cimetidine is also similar. We can see this is a crystalline intermediate, amorphous intermediate, but 1 week later, and also you see a lot of the crystalline peaks. So this is also show you very, very low stability of these drugs. So we have to do something, right? To do something to improve their low stability. In this case, we have different strategies to improve the poor solubility, stability of these amorphous compounds. In this case, solid dispersion, we can see that different solid dispersions from eutectic mixture, solid in solution, complex glass solution, amorphous suspension, and so on. There are so many different types. Basically, we're going to talk more about amorphous suspensions. You use a drug and polymer and mix it together, and then you only get one phase, and it is amorphous mixture. In this case, we call it amorphous solid dispersions. Glass or amorphous solutions is the most suitable for increasing dissolution. Why? Because of what? Because they mix very nicely. They only have one phase, and the drug is amorphous. The drug amorphous, we already see the amorphous drug usually show a much higher dissolution rate, right? And this one will give you an advantage of increase in the dissolution. And also the polymers, you can use the water-soluble polymers to improve the water solubility of the compounds. So basically, we're going to focus on more about the glass solution or amorphous solid dispersion. This figure shows you how we develop formulations, especially amorphous formulations. We start from here, the new drug. The new drug, you select excipients or some other useful conformers. And then if it is similarly stable, yes, you can then go forward. Small scale fusion, and then prepare lab scale materials, and then finish all the characterizations. The different characterization, if it is amorphous or not, if it is yes, and if it is just one TG, it means they only have one phase here in this table. Usually, if you have 2 TGs, usually you have at least 2 phases in your sample. So if it is 1 TG and TG is over 70 degrees, it means it is stable. Usually it means stable, but sometimes it is also not very, very, very true. So basically, you have to figure out by yourself. This is just based on our generally experience. If the TG is over 70 degrees, and if your answer is yes, okay, you are so lucky. And then you can scale up. Because from here you prepared in small scale, and here you scale up and do a lot of dissolution test. If you are lucky again, if the dissolution rate is very high, and then you get stability is also very less, and okay, you are super lucky. All of this stuff is very good, right? It's very good, and then you can get another scale and then prepare commercial scale. But as we know, they are very, very difficult to get all yes through this whole picture. But if you get a lot of no, and then you have to go back. Not amorphous, you then go back, and you may choose different preparation methods, because we already discussed the different methods matters. And sometimes you even should choose a new excipients. So there's a lot of no. But because you generally you won't be super lucky to get all yes. So this is why developing a new product into the market is usually takes over 10 years and a lot of money, because you need to do a lot of the experiments. So basically it is very challenging. And if you prepare the glass solution or amorphous solid dispersion products successfully, and from the scanning TEM, from SEM, you can see from here, these particles, crystalline particles, and then amorphous particles, they show totally different surface, right? And usually this one is more soluble. And basically you have you can choose a spray drying, melting extrusion, or supercritical freeze, and or co-precipitation. But generally the first two this first two is more suitable for commercial products preparation. This two is too expensive, and usually you have a lot of problems. For example, the third one is too expensive, and the first one you have to check the solvents. The solvents in your product is already take out or not. So this is also a lot of the problems. The first two is more common use in industry. And if you are still in the lab scale, the ball milling will be a very nice method, because you only need to spend a little bit of powders or samples. You can do experiment. But for this, for the other methods, you should spend a lot of amount of the powders. So ball milling will be very nice for the lab scale. But if you want to scale up, this will be very, very challenging. Here, this is a rough picture of show you how hot melting extrusion works. This is from the materials. You just put your powders here, and then this is the extruder and rotating all the time, and the heating also auto heating your samples, and then mix it together. You will get out. This sometimes you have to use a cooling system to make it amorphous, right? And here you get your sample. Here your sample. Usually it is like noodles. But sometimes we have to beer it and then to get small particles, right? And here you can collect with other machines. And here, this is the picture of how it works. And you put your sample, get inside, and then get your compounds or amorphous products get out of from this extruder. And we can see this is the products already. These products just like noodles, and this is the first scan, rough scan of these samples after preparation. And this is turbulent limit and PVP 1:1 weight ratio. And this is ACM of these products. And legacy dipping PVP, it's just like noodles, okay. This is ACM of this product. Okay, after the preparation, you have to check it is amorphous or not. And again, we use X-ray, right? XRPD. And this is the product from leafy dipping, black curves. We can see this is crystalline compound. They show very obvious peaks, and the red one, crystalline, This is a physical mixture of the drug and the PVP, the excipient. We can see this is also show the obvious peaks. And the blue one, if you use hot melting extrusion, you will get the blue one. The blue one already getting amorphous, right? This is already amorphous. So this is how we check it. And this take-home message too. There are already some amorphous formulations in the market, and hot melting extrusion is the most used preparation method for commercial products. So we can see a lot of commercial products using the HME method. And currently, I also trying to buy a HME machine in Wenzhou in my laboratory. And section 4, alternatives to drug polymer systems, including drug-drug combination. In this case, actually, we also call it coamorphous systems. Drug-drug coamorphous and drug conformal coamorphous. Here, let's see. Drug-drug combination. Here, I will give you guys 2 examples: the leprosy and simtidine. These 2 drugs already in the market, of course. This is the basic information of these 2 compounds. The leprosy used for this one, right? Already, you guys, I'm sure you guys know this. But its side effect is that gastrointestinal disorders, and the simtidine can be used for these disorders. So it is very nice, these 2 drugs combined together. This is why we do like this. Drug, we use these 2 compounds mixed together and then trying to prepare amorphous compounds. Here, individual APIs before and after meal. This is non-milled. This is before milled crystalline leprosy, crystalline simtidine. We can see the peaks, and milled leprosy. The pure leprosy cannot be amorphous after milling. As we already discussed, sometimes you cannot use bromine to prepare amorphous compounds. This is an example. We failed. And the simtidine succeed, right? Simtidine we succeed. For these 2 compounds, we doing like this. And then we also using DSC, figure out the TG of these compounds. The TG of the simtidine is 36, and this one is super low. This is why we can't use bromine to prepare amorphous leprosy, because the TG is super low. Usually for these compounds, you cannot use bromine to prepare amorphous. In this case, we used quench cold, right? And here we use mixtures 1:2 model ratios, 1:1 model ratios, and 2:1 model ratios. Different model ratios and the 3 samples we prepared using bromine, and all of them became amorphous. And the TG shows here, and the highest TG we can observe the 1:2 model ratio, 40 degrees, and then we can go ahead. And the physical stability study shows that after the preparation of the amorphous, we store at a dry condition for 2 months. 2 months later, we checked with XRPD. We can see from here the 1:2 model ratios already show this recrystalline peaks here, right? And 2:1, they're the same. This is very obvious recrystalline position, recrystalline peaks. And the most stable one is 1:1 model ratio. So basically, from this experiment, we can see that not the highest TG after preparation shows the most stable, the highest stabilization. Still stable after 6 months. So the TG is only give you a rough idea how stable it is, but you cannot only based on this information trying to judge it is stable or not, because you need to do physical stability study. And the more important, because we are trying to improve the water solubility of these drugs, we can see the ADR of these compounds. We can see from here, for leprosy, the ADR, the dissolution rate of crystalline is here, and this is the coamorphous one, right? The coamorphous one is much higher than the a crystalline one. And also here, cimetidine, we can see the crystalline cimetidine dissolves very slow, and the coamorphous one much faster. And pure amorphous one is a little bit higher, but not so high as coamorphous. This is because of what? This is likely immediate crystallization upon dissolution, because once you dissolution process, the amorphous cimetidine recrystallized very fast and then decrease the dissolution rate. So basically, if we compare the amorphous leprosine and the cimetidine, we can see the dissolution rate is almost the same. So we can see, we can have say this of synchronized release of these two drugs. This is very good. And here we also see quench cooling, using quench cooling method to prepare amorphous and coamorphous samples. We can see all of them get amorphous. This is indomethacin and leprosine. These are another two drugs. We also get similar information from as leprosine and cimetidine. As we can see, this 1:1 molar is also much stable than this one. And this because of what? Because 1:1 molar ratio is much more stable, like this 1:1, right? Because this is a hydrogen and bonding together. So this is the most stable molar ratio. And the DSC shows you the transition and glass transition temperatures like 20 or 30 degrees. In this case, basically from my experience, this is not super stable, because usually if room temperature is almost 25 degrees, if your TG is around 25 degrees, what this means? It means your sample just store at room temperature, it is already finished glass transition. And this is not very stable for amorphous compounds, right? So this is not very good. And for the experimental and Gordon Trainer teaching, Gordon Trainer is a scientist, very famous in this area. And this guy developed a formulation trying to calculate the TG of two compounds theoretically. So this one is very useful. In this case, if you want to 1 mole ratio, you can just use this formulation, calculate the TG of the mixtures. But in our case, it is not very nice to use this formula, because of what? Because the compound, these two compounds has the molecular interactions, and then makes this formula is not so nice. And if your molar ratio is not 1:1 molar ratio, in this case, you have to use this one. The first TG should be coamorphous, and the second TG should be the excess component. Because if you use 1:2, because in this case, 1:1 molar ratio, this forms coamorphous, and then the other excess components formed like TG2. In this case, you can get a more trustworthy theoretical TG like this. So this is almost the same as the experimental TG, right? This is very useful. And again, our topic is trying to increase the dissolution rate. Intrinsic dissolution shows leprosine and indomethacin, all of them amorphous one increased compared to their crystalline compounds, right? So this is also, again, we can see this is synchronized drug release, these two compounds together, because these two compounds binding together by hydrogen bonding. And if these compounds want to dissolve, they should destroy the hydrogen bonding together and destroy this bonding. And then there should be like 1 molecular and 1 molecular. So this dissolution rate is almost the same. So this is why it is always show synchronized drug release. And we already discussed the drug-to-drug combinations. And then here we introduce you drug amino acids. drug amino acids, because of what? Because amino acids usually can interact on a molecular level with drugs, and histidine and arginine usually able to form amorphous phase upon freeze drying. And more important, the molecular, the drug and the receptor always shows the molecular interactions together. And in this case, we tried different amino acids as conformers. Besides two drugs we can have here, indomethacin, naproxen, carbamazepine, and usually their receptors always shows arginine and tryptophan and so on. These drugs can combine with the amino acids in their receptors. So we tried these different conformers. Here, like this is receptors, right? Receptors and the indomethacin combining with arginine together. So this is why we should have this hypothesis. Here we choose carbamazepine. Carbamazepine and indomethacin, these two model drugs, and we choose phenylalanine, tryptophan, arginine, these four amino acids as conformers. Then we use the bromine to prepare amorphous. And we can see from this figure, all of them became amorphous systems, right? There's no obvious peaks here. So all of them became amorphous. And then we continue to use DSC trying to figure out the TG information. The pure indomethacin, the TG is around 36, and carbamazepine 55, and the co-amorphous samples, they showed much higher TG compared to pure compound, right? Much higher, and basically this is a very good. And also we can only see one TG for these samples. One TG means one phase. It is very, very nice. We can call it co-amorphous systems. And physical stability, we can see carbamazepine only stored for 7 days and they recrystallize very obviously, right? And indomethacin 7 days also recrystallized. But for the co-amorphous systems, except this one, all of the others remained amorphous. So basically, it means the existence of the conformers can be used as a stabilizers to improve the physical stability of this pure amorphous compound. And then also we finished the dissolution test. Crystalline indomethacin is here dissolved with slow indomethacin, amorphous indomethacin a little bit higher, but the highest is that indomethacin phenylalanine. And also this is a PUP. PUP, we just introduced couple minutes ago. This means solid amorphous solid dispersions. Basically, the co-amorphous systems, the dissolution rate of the co-amorphous system is almost similar with the indomethacin PUP. So let's get a summary. Highly stable co-amorphous mixtures improve dissolution, and it is comparable with PUP in some dispersions. And the weight ratio is very high from the different ratios. Usually, if we want to get the highest physical stability, usually we use 1-to-1 model ratio. Okay, 1-to-1 model ratio or 1-to-1-to-1 model ratio. This is the most stable. Take home message 3: small molecules, including the drugs and also amino acids, can also be used and to make co-amorphous systems. And this can be other, the molecules can be the second drug or also other amino acids. Basically, until today, there are also some other small molecules such as organic acids and other molecules can be used as well as amino acids. So in this research area, there are a lot of new progress approached in each year. And section 5, I would like to give you a case study in amorphous formulations. A case study in amorphous formulations. Basically, it is still from coamorphous formulations. This is from my own work. Coamorphous systems improve the physical stability of amorphous drugs and dissolution rates. This is the purpose, right? And here, give you rough introduction about what's the difference. Let's get a summary, actually, summary of the talk of today. Crystalline drug, we can see from here, the middle one. Crystalline drug usually shows no solubility, right? But it is very stable because the structure and the non-range order is very stable. But the low solubility, we want to improve it, right? And then we prepare amorphous drug. We prepare amorphous drug. This is usually shows very high solubility, but the physical stability is very low. So this is the disadvantages, right? But if you want to prepare or develop a product into the market, we should combine these two together, right? Both higher solubility and higher physical stability. How? And then we introduce crystalline conformer to prepare coamorphous systems. Coamorphous systems is a compound, right? A crystalline conformer and the crystalline drug mixed together and then form one phase of amorphous systems. One phase of amorphous systems, in this case, we can get higher solubility and also higher physical stability. So this is why we want to develop coamorphous systems. Coamorphous systems, usually we can see, at least there are two different kinds of coamorphous systems. Coamorphous one, the drug and the conformer, they just mix together. They don't have molecular interactions. And the second type is that the drug and the conformer, they have molecular interactions. For example, hydrogen bonding, salt formation, and so on, right? Different molecular interactions mixed together, and then you also can form the coamorphous. And in this case, they're just physical mixed together. They don't have any molecular interactions. Why we should mention this? Because whether or not the molecular interactions between the drug and the conformer usually show a very important effect on the performance of coamorphous systems, both in solubility and dissolution and stability. And the conformers can be drugs and amino acids, organic acids, and so on. We already discussed about this, right? And in this study, I chosen aspartame as the conformer. Aspartame. Why we choose aspartame? Aspartame is used very widely and today from drinks, soft drinks, and a lot of other foods used as sweeteners. So it is acceptable in normal life. So it's very safe. The basic information of the aspartame is here. The molecular weight is around 300, and melting point is very high, and also it is very safe. So I use this compound as a conformer, and then used 3 model drugs. 3 model drugs called mebendazole. Mebendazole, I'm not sure how many of you still remember this drug. This is just at the beginning of some of the slides. We compared the solubility of mebendazole and calcium carbonate, right? Still remember? Mebendazole and tadalafil and piracicam. Mebendazole, we already know that the solubility is very low, right? Tadalafil is almost the same as mebendazole. Piracicam is a little bit higher, but still very low solubility. So I choose these 3 models as drugs. And the other reason is that mebendazole is a basic drug, tadalafil neutral one, and piroxicam acidic one. So I just use different types of the compounds. Both of them belong to BCS2 drugs. And then I use the ball milling to prepare the samples. Ball milling is just like it's a very small machine actually. They have the two arms and shaking all the time, and then you have to use two balls, two stainless balls inside, and then using the mechanical power to be your sample, your powder. So basically, I use 50 milligram powder in the jars, and then the water ratio is also 1:1. And then this is the time and the shaking frequency. And after preparation, we use XRBD and DSC trying to figure out it is amorphous or not, and also using TSC to figure out the temperature of the glass transition, and also figure out it is one phase or two phases. And more important, we always have to focus our topic, right? Our purpose. Our purpose is trying to improve the solubility of these three drugs, right? So this one is very important. And the powder dissolution studies, we use just this USP two apparatus to finish this study, and at different time points, just withdraw the samples, use HPLC to figure out the drug concentration in the medium. And also, let's see the results here. Here, this is the result of the XRD. XRD, this ABC. This A means the crystalline structure, crystalline drugs, and here this is before meaning, right? This is the conformers, the three conformers, aspartame and the aspartic acid and phenolalanine. And also this is a conformer after ball milling. As we can see, the conformers, aspartame, aspartic acid, and phenolalanine, all these three conformers cannot be amorphous ball milling alone. And here from the D, we can see from here, mebendazole can be amorphous or known by ADCF. You don't have to use conformer, right? And the conformer aspartame can be amorphous as well. Mebendazole aspartic acid, this amino acid cannot be amorphous. And the phenolalanine, this is also cannot be amorphous. And the physical mixture of the aspartame and the phenolalanine, okay, failed again. And this is the case of the mebendazole. And here, this is the case of tadalafil. Tadalafil here can be amorphous or no again, but we will explain why it is not very good to use it alone. Tadalafil aspartame succeeds, right? And tadalafil aspartic acid failed. So only for the three conformers, only aspartame shows the high and the best conformer performance. And piroxicam cannot be amorphous or known, right? We can see the peaks here after milling. We can see from here, right? And the piroxicam with aspartame, very nice. It is already amorphous. And aspartic acid and the phenolalanine and the physical mixture of these two, all of them failed because we can see an obvious peaks here. So basically, from XRD results, we can say mebendazole and tadalafil can be amorphous or known, but if you use aspartame, it can be also amorphous. And in the case of the piroxicam, you have to use aspartame as a conformer because all the other samples failed to be amorphous except this one, right? So in this case, we can make a summary. Aspartame showed very nice conformal performance to be amorphous. And here we have the DSC results. DSC results, this is the pure compounds. We have the DSC here, have TG here, and also the coform, the mixtures, 1 to 1 mole ratio, right? And then we have the TG here. And this is a steric TG according to Gordon-Taylor equation. And this is from theoretical, right? Theoretical TG. We can see it's almost the same, This means there are no molecular interactions between the drug and the coformer. And 1 TG usually indicates that this is one phase of these 3 samples, only one phase. One phase means it is become co-amorphous successfully. And here we use FTNR to figure out whether there are molecular interactions between the drug and the compounds. As we can see, almost the same, only all 3 samples. And here the most important part, the powder dissolution, the dissolution test. The powder dissolution test we have done 24 hours, right? 24 hours. And here this is the figure A is the case of the mebendazole, and the figure B is the case of tadalafil, and the figure C is the case of piroxicam. So from the figure A, we can see the crystalline mebendazole, the black dots, we can see they dissolved very, very slow, right? This is where we see the water solubility of mebendazole is much lower than calcium carbolate, right? Because this is microgram per milliliter. You can see that here is no more than 1, right? And 0.5 or 4. And the red one, amorphous mebendazole. Amorphous mebendazole, they dissolved and increased the dissolution rate of the crystalline and mebendazole. And the co-amorphous sample with aspartame, right, dissolved very fast, and then recrystallized. And the ferrol concentration of after 24 hours is almost the same as amorphous one. So basically, from this case, we can see mebendazole co-amorphous showed very nice supersaturation curves. So in this case, it is very nice for these drugs to improve the bioavailability of these drugs after oral administration. And in the case of tadalafil, a similar phenomenon also were observed. We can see from here, the co-amorphous dissolve much faster, right? Much faster. And in the case of piroxicam, because there has no amorphous piroxicam, so there are only 2 samples here. And the piroxicam crystalline black dots start from here, dissolved a little bit fast, but also recrystallized. But for co-amorphous samples, dissolved much faster, because at the beginning of the 1 or 2 minutes, the concentration is already very high. This means dissolved very, very fast, and always maintain this concentration. So basically, this is also showed co-amorphous dissolved much faster than crystalline one. But this case is a little bit different. We don't have too much time, so I'm not going to explain too much in detail. This is because crystalline piroxicam or amorphous piroxicam formed monohydrates in the water. So the co-amorphous one dissolved very fast and formed monohydrates very fast. So the concentration is always like this. And the crystalline one dissolved very fast and then formed monohydrates decreased and to the same concentration like this. So this is a different case from with this former 2. And also the physical stability study after 3 months. After 3 months, we can see the pure amorphous of mebendazole recrystallized. This is why we cannot use pure amorphous, right? And here this is stable, but in this case, mebendazole, the pure amorphous is not stable at all. So we have to use aspartame as a conformer to improve the physical stability study, increase the physical stability. And from this study, we gained a lot of interesting information, as well as other data. We applied PCT patent in the 2018, and currently this case already we got the lessons. And this one is very interesting job, and yes, it's very close to industry. So not just academia research. We use this patent already my supervisors from my PhD study, and we already established a company in Copenhagen, Denmark, and now we already have a few funding from the Danish innovation funding, and also other money from the pharmaceutical companies. So we are going to bring these products into market in the following few years. It is very interesting. And acknowledgement, this is the full picture of all the work we of the slides today. The Professor Thomas Ratz, he's very famous scientist worldwide, and also the Holger Gergens and Corbinian and Nobleman. Now the Corbinian already with some other co-workers, we were working together on the companies. So basically, he spent a little bit time in the university and most of the time in the industry already. And only for fun, what we are doing, you guys, we can have a guess what we are doing here. Basically, this is liquid nitrogen. Liquid nitrogen, we can see here, and we are preparing something, right? Just forget the beer, right? Forget the beer here. We are doing something, and you can have a guess what we are doing. Here, like the same, show your big picture here. This is liquid nitrogen, and we always stirring. By the way, we are doing amorphous ice cream. Amorphous ice cream. What we are doing here? We just heating the ice cream and melting the stuff, and then use liquid nitrogen cooling it down and quench cooling, right? Quench cooling it down, and then we will get amorphous ice cream. Amorphous ice cream is much more delicious than normal ice cream. Okay, this is much more delicious. And here back again, which one is sweeter? Which sugar is more delicious? Of course, it is amorphous sugar, right? Because it's all much faster, and you turn with much more sugar molecules at the same time. So this is much more sweeter. Basically, this is all the slides for my presentation. Thank you all for your listening, and hope you enjoy it. Thank you.
Thank you so much.
Thank you.
Yeah. Yeah. Thank you.
Thank you, sir.